Hello everyone. I hope you've really spent a lot of time on section 7.1 because that's really the basis for the rest of the chapter. If you can get those concepts down, this won't be hard at all. This will be just an extension of 7.1. Now we're going to actually do some hypothesis testing, and to start off with something you're most familiar with, we're going to do hypothesis testing for the mean. And section 7.2 includes when we know the population standard deviation. In section 7.3, we're going to talk about what we need to do when we don't know the population standard deviation. But that will come when it comes. This is where we are. Hopefully you spent enough time, because you need to be a star when it comes to 7.1, the introduction to hypothesis testing. With that done, then we're going to move on to 7.2, and once you get that down, 7.3 will be just an asterisk to you. These are what we're going to try to do. We're going to work with p-values. We're going to use p-values by themselves. We can use p-values for a z-test. Now we can use the z-test, by the way, only when this population standard deviation is known. So you have to keep that in mind, because in 7.3 we'll be talking about a similar thing, but when the population standard deviation sigma is not known. Also, we'll talk about critical values and rejection regions. Of course, we're talking about the standard normal distribution, although I'm going to give you some tips on how you can do it without resorting to the standard normal distribution. And how to use rejection regions. Because what we want to do is we want to do hypothesis testing on a mean. So here we go. We're going to use a p-value. P stands for probability. And using that, we'll make a conclusion about the hypothesis test. And to do that, we're going to compare, we're going to compare the p-value that we get with alpha, which is the level of significance. And here's how we do it. And I'm going to change this just slightly, because I checked with someone I trust, and he said he usually uses p less than alpha. It's not going to make a big difference, really. You can use this just as well, and since my friend said p less than alpha is usually the way to go, we'll go that way too. And if p is greater than or equal to alpha, then we'll fail to reject the null hypothesis. So let's get started. Suppose we do get a p-value. Now we haven't yet, but suppose we did, and that p-value is 0.0237. What will be your decision if the level of significance alpha is 0.05? Remember, what you're checking is, can you reject the null hypothesis? And that'll be if the p-value is less than alpha. So fill it in. The p-value here is 0.0237. And question, is it less than alpha, which is in this case 0.05? Well, yes, that is true. So we're going to reject the null hypothesis. Oops, just a second. What about if this is the alpha instead? We'll do the same thing. Is p less than alpha? P is 0.0237. Is that less than 0.05? 0.01. No. Fail to reject the null hypothesis. After you do that, after deciding the standardized test statistic, which in this case will be a z because we'll know the population standard deviation, we're going to find the test statistics corresponding area. So we're going to do something like this, and we're going to find out where the test statistic is. And let's suppose the test statistic is here. And we'll say that's the, and I like to use this notation, z with a small t, that way we know it is the test z statistic. And to get the p-value, we're going to do something we've done many times in the past. We're going to find what the probability is of getting a value of this value or higher even. For a left-tailed test, we'll be talking about the area in the left tail. We'll be calculating that. Remember, just as a hint or a reminder, normal CDF is what you'll use because you want to find the probability. And for normal CDF, if it's the left tail, it will be negative infinity to whatever your test value is. And since we're working with z values, it has a mean of 0 and a standard deviation of 1. That's how you get your p-value for a left-tailed test. How about a right-tailed test? Not too much different. For this one, there we are. We'll use normal CDF since we're talking about probabilities. But this time we start at z sub t because it's a right-tailed test. And we're going to go to positive infinity. And of course, since we're working with z values, 0 and 1. For a two-tailed test, now this is a little bit different. Similar but different, because when you find that p expression that you found from one of these, you might find this area or you might find this area depending on where your value is that you're comparing. And when you get this p-value, or to get this p-value, you're going to double the area you find in that tail with the standardized test statistic. We'll do some examples, so don't worry about it. So let's take a look at this. Find the p-value. So we're looking for this. It's a left-tailed test. So right away I'm going to draw a little picture here. Left-tailed test looks something like that. And we've got a test statistic of negative 2.23. So our test statistic, negative 2.23. And we want the area to the left. So we're going to take normal CDF, negative infinity to the negative 2.23, 0 and 1 because we're using z values, although we don't always have to, but in this case we are. And when we get that, we're going to compare it with alpha. So let's see. It seems the area back on that part, where's my cursor? There we go. The area back here is 0.0129. So remember, we're going to reject if p is less than alpha. P is 0.0129. Is that less than 0.01? Not quite. So, fail to reject. Got that? All right. So remember, to get that, since it was a left-tailed test, start at negative infinity, go up to our test z value, 0 and 1. If this is z, then use 0 and 1 here. If it's not, you'll have to use other values, but we'll get to that in time. So we failed to reject the null hypothesis. Let's try another one. We want to find the p-value for a two-tailed hypothesis test. So let's go with a picture here. We've got two tails this time. Now we want to find out whether we're going to reject the null hypothesis with an alpha of 0.05, which you'll find quite often. Now our z value, our z statistic, is 2.14. Well, that happens to be out here, so we're talking about 2.14. So we'll be finding this area right there. So to find that area, defined areas, normal CDF, and I'm going to have to go down to the next line. We want to go from 2.14 to positive infinity. Remember, my shortcut is just a bunch of 9s, because that'll simulate infinity. And since we are using z values, this is a z test value, then we'll have 0 and 1 closing out the normal CDF. And when we get that, remember, the value we find from this area, right here, to get the p-value, we're going to have to double that because it's a two-tailed test. So using our trusty TI-84 and 2.14 and the right tail, we'll get a value, but if we are a little bit clever, we can actually start our calculations or our calculator to do this at the very beginning. We know we're going to multiply by 2 because it's a two-tailed test, so 2 times. And then you can go to normal CDF, and it won't harm the 2. The 2 will stay there. Put in your parameters for normal CDF, and this is the p-value after we multiplied the area by 2. Now, what do? Is this less, is that less than 0.05? Yes. So we're going to reject the null hypothesis. So this is what we did with the calculator. Remember, if you have a two-tailed test, you can put this 2 out here, put the times, and then find your normal CDF function. And you'll get your p-value right away. Remember, don't multiply by 2 when you have a left or right-tailed test. Only the two-tailed test. Two-tailed test, multiply by 2. Okay. So we rejected the null hypothesis with that two-tailed test. Next, how do we get that? Because just a moment ago we said the test z statistic was 2.14, right? Well, how do we get 2.14? This is how we get 2.14. Take the mean from the sample minus the population mean we're comparing it against, and divide by the standard error, not just the standard deviation, which we know, but the standard error, which is the standard deviation divided by the square root of the sample size. That's your standardized test statistic, and this one is a good one to write down. I wouldn't suggest getting a tattoo, but do get it tattooed sort of in your memory. Remember, you have to have a random sample, and either it's normally distributed, someone tells you that, or the sample size is greater than or equal to 30. And there's your standard error, which we use instead of just the standard deviation. All right, let's summarize this. You make sure that you know the population standard deviation. You've got that. The sample's random, and you have one possibility. Either the population is normal, or you have a sample size large enough to cover for that because of the central limit theorem. Once you do this, you're ready to go. If you don't have it, you stop dead. You're gone. But if you can, you go on. Remember, you're going to look for the claim, state it mathematically and verbally, write the opposite of that claim, and then identify the null and alternate hypotheses. Remember, the null one has an equal somewhere in it, and the alternative is the leftover hypothesis. Before you do anything else, before you do a sample even, specify the level of significance that you care about. Otherwise, it's called cheating. Number 4, find the standardized test statistic. Again, this is the mean from your sample. This is what we're comparing it against, and the standard error is in the denominator. Next, you find the area that corresponds to that z. Now, notice I use z sub t, that way I don't get z's mixed up, because later we're going to have critical values of z, and you don't want to get mixed up between the two. If you have z sub t, you know it's a test z statistic. With this found, you want to find the area that corresponds to z. And then find the p-value. If it's a left or right-tailed test, you've got it. The area is the p-value. If it's a two-tailed test, you have to multiply the area by 2 to get the p-value. Left-tailed test, just the area straight off in the left side. Right-tailed test, just the area. For a two-tailed test, remember, you multiply by 2. And maybe to keep from forgetting, when you get to your calculator, you put the 2 in first when you have a two-tailed test. Then go to the normal CDF and work from there. Once you've got that done, you decide whether to reject or not. Remember, the wording is reject the null hypothesis or fail to reject the null hypothesis. And number 8, interpret the decision in context of the original claim. That's why when you wrote the original null and alternate hypothesis, you labeled which one was the claim. Because when you get your result, whether you're rejecting or not rejecting the null hypothesis, you have to describe your answer in terms of what the claim was. All right. Now let's get down to brass tacks. How does this actually work? So you might want to pause right here and read through this. I'm not going to read it word for word. That would be boring, right? Now, as I'm reading through this, I notice this tells me about races, and then it says the pit crew claims. So here we are. The claim is coming. The mean pit stop time. So we're talking about mu. The mean pit stop time is less than 13 seconds. So here's our claim. the mean is less than 13 seconds. Yes, I put the seconds there. That reminds me of what we're actually working with. Next, what's the opposite of that? Well, it'd be the mu is greater than or equal to 13 seconds. What's next? Sort these out. What is the null hypothesis? Well, the second one has equals, so that will be mu is greater than or equal to 13 seconds, which we know then the alternate hypothesis has to be less than 13 seconds. So we think we're in good shape here. We've forgotten one thing. You want to write down which one was the claim. Well, this one, the first one, was the claim, so we're going to make a note here. The alternate hypothesis this time is the claim. Now, where do we go from here? Well, I'm going to pick out some other things. After we see what the claim is, which is right here, we've got some numbers that we get. Where's my cursor? There we go. The sample size is going to be 32 pit stops. And when we do that check, we find that the mean of our sample is 12.9 seconds for the pit stop times. Also, it says the population standard deviation, good, is 0.19 seconds. Is there enough evidence to support the claim? Notice there's something missing that we'd really like. It doesn't say that we've got a normal distribution for those pit stop times. However, thanks to the central limit theorem, our sample size is over 30, so we have a normal distribution of those sample means. Okay, so alpha equals 0.01. We're going to find our p-value, and our p-value will be compared against the alpha value. So let's catch up. So we've got population standard deviation known. We've got that. We have the sample size greater than 30, so we can use the z-test. The claim is the mean is less than 13, so here we have the null and alternate hypotheses. And we've labeled the claim as the alternate hypothesis. The level of significance is 0.01. We're ready to use that. The standardized test statistic. Well, 12.9 was the X bar. 13 is the value we're comparing it against. Here is the population standard deviation we knew, and our sample size, we take the square root of that and divide it into the population standard deviation. Use our handy calculator, we get negative 2.98. Now we have to find the p-value. Well, draw our picture. What kind of a test was it? The alternate hypothesis tells us what kind of a test it is. It's a left-tailed test. So in our picture, we can draw this in, and our z-value is negative 2.98. So we need to find this area, which will be our p-value. So p equals, and for probabilities, we use normal CDF, since we know the population standard deviation. From the left, we have negative infinity. We're going to go up to negative 2.98. Since we're talking about z values, we have the z over here. Test value. We'll have a 0 and a 1 here. So here we go. Normal CDF tells us this is the p-value. And we're comparing it against an alpha of 0.01. Is this less than this? Yes. Since it is less than that, you reject the null hypothesis. What does that mean, though? Just because we reject it, it doesn't mean we have the answer, because we have to take it back to the claim. And this is a tip. We're going to sneak this in. If you want to do it without going to the z value, you could do it this way. If you think of your distribution as having a mean of 13 and a standard deviation of 0.19, we can do all of this in one step. This is your negative infinity. This is your value on the left-hand side. And here we have our standard deviation, which we know, and the population, or the size of our sample. And there's our p-value. Same thing we got using the z-value. You can use either method you want, they'll both work. And this is what we really wanted to know. What can we say about that claim? Remember, the pit stop crew was saying that they average less than 13 seconds. We rejected the null. What does that mean? It means there is enough evidence at the 1% level. What is that? That's the alpha, the level of significance. And since this value up here is less than that value, we reject the null, and that means that we have evidence to support the claim that the pit stop time is less than 13 seconds. So hooray for the pit stop crew. It looks as though they're correct. Now, are we sure? No. But our sample statistic suggests that yes, we can support that claim. Let's try another one. We've got a study of U.S. homes, and the mean, we're going to write this down here. Here we go. So the mean is 68.3 degrees Fahrenheit. Now, what do we have? You think that's incorrect. So your claim is that it's not 68.3 Fahrenheit. Since the first one on the top has equal, that's your null hypothesis. This is your alternate hypothesis. And we're going to check to see whether that works or not. We're going to use an alpha this time, as we often do, of 0.05. We've got the population standard deviation. That's good. So it looks as though everything is good for us. So what is our p-value? Well, we can use it. We can get the z-test statistic if we want, which would be 67.2 minus 68.3 we're comparing it against. And the population standard deviation was 3.5. And we've got the square root of our sample size, which was 25 indoor homes. Notice that the population is normally distributed. This time we really need this because our sample size is only 25. It's not 30 or over. But this saves us being normally distributed, so we can use a z-test in this case. And then with that z-value, you can use normal CDF to figure out what this is. In fact, let's erase that a second. We're going to use this z-value to find the area. And when we get the area, we're going to multiply by 2 to get our p-value. Okay, let's clean this up. So we know the Population standard deviation, check. Random sample, check. Normally distributed, check. We're ready to go. So you can use the z-test. If we do, then we know how to do that. We're going to claim that the mean is different. That means not equal to. So that becomes the alternate. And this is the equal part, so that's the null hypothesis. Label the claim, because we're going to need that at the end to make our final statement. So the level of significance is 0.05, which you'll see quite often. Standardized test statistic, there's our 67.2 that I pointed you to earlier. Here's what we're comparing it against, the mu. And there's our population standard deviation, square root of the sample size, and there is our z-test statistic. And we can get this directly. We know since it's a two-sided test, because it was not equal, is a claim, we're going to have to multiply the area by 2. So we'll put the 2 there, times, and we'll go to normal CDF. So this 67.2 is on the left side, so we'll get the area on the left side. So we'll start with negative infinity, 67.2. There should be a comma, by the way. 68.3 is the mean that we are using. Here's our standard error, 3.5 divided by the square root of 25. And after it's multiplied by 2, we get this for our p-value. Unfortunately, that's not less than alpha. Our alpha was 0.05, but our p-value is 1164, 0.1164. Fail to reject. It's not less than alpha, the level of significance. And there's some good wording. You might want to copy this again. Get practice using the correct wording. Another way we could do this, I haven't shown you yet, but there is a second way of doing this. And in some cases, it might be faster. Now, what you'll need to do is, where's my cursor? There it is. Hit the stat key, move over to the tests submenu, select z-test, which I think is number 1. You can double check me on that, but I think it's number 1 under the test submenu. Then enter the data. Notice it has a line here that says input data or stats. Well, we don't have the individual data, but we do have the stats. So make sure for this one, since we didn't have the data, that this stats is highlighted. Then we'll put in the value we're comparing it against, put our standard deviation for the population that we're given, and this is the mean from our sample, this is the size of our sample, and this is the kind of test we're doing. Remember, if it isn't highlighted for the test that you're performing, you have to change it just the way you'd have to change this up here, depending on whether you had the data or just the stats. Once you do that, come down here to calculate, hit enter, and here's what you get. This tells you what kind of test you're doing. This tells you what the standardized test statistic would be. This gives you your p-value. This gives you the mean that you got from your sample and your sample size. You've got everything right there. Since it's less than 0.05, you're going to reject the null. Reject the null. Now, we're going to show you how you can do it a little bit differently. You can use either method you like, but it's good sometimes to have different ways of doing the same thing. In this one, we're working with rejection regions and critical values. Now remember in the one before, you find the test statistic, and that gets you to your p-value. With this one, we're going to first draw our picture, of course. We're going to find out where the cutoffs are. Where are the regions where the results are improbable? The range of values for which the null hypothesis is not probable. That doesn't mean it's impossible, just improbable. If the standardized test statistic falls in that region, the null hypothesis is rejected. In other words, if this is our critical z value right here, if our test statistic falls in here, then we're going to reject the null. And a similar thing is true working from the left side or from both sides. Critical value, z sub 0. Now, you'll see this quite a few places. I like to use z sub c, so I know I'm talking about a critical value in the z line. It shows you where the rejection region is separated from the non-rejection region. We'll show you how to do that. So first of all, how do you do it? All right, first, you need the level of significance, alpha. Decide which kind of test it is, left, right, or two-tailed. Next, what is the critical value or values? I'm going to make this z sub c. If you like that, fine. If you like z sub 0, that's fine with me. Now, when it's left-tailed, you're going to find the z-score that corresponds to an area of alpha. So we're starting with alpha to get our critical value. In the other one, we took our test statistic and we find the p-value. Here we're going to start with alpha instead of alpha at the end. If it's right-tailed, then it's going to be 1 minus alpha. It'll be the other side. If it's two-tailed, remember we've got two parts, two areas actually where we might reject the null hypothesis. And we take the alpha and divide it by 2, and 1 minus that will give us the other area. Sketch the distribution, whether it's left-tailed or right-tailed or a two-tailed test. And you want to find where these critical points are for your test. Remember, I'm using z sub c just so you don't get confused. All right, so find the critical value in the rejection region for a left-tailed test with alpha equals 0.01. All right, first picture. All right, there's our normal distribution. We've got a left-tailed test, so our rejection region is going to be on the left side. And this cutoff point is a critical value, and we're going to compare this with our test statistic. Now, it's a left-tailed test, so we're going to reject the null hypothesis if the test statistic falls over here. In other words, for this left-tailed test, is it less than the critical value? Because this is our rejection region. In this case, well, let's keep on going. So here's our picture. 0.01, we find the critical z value is negative 2.33. Remember, in case you're missing this, you work it like this. You put the area here for inverse normal, 0 and 1, because you're working with z values. And that will give you your critical value. And now, what is your test statistic? Is it over here or is it over here? Now we're not going to finish that because we don't have the actual numbers. We're going to try this again with a different version of alpha, the level of significance. Draw a picture. We've got a two-tailed test, so we've actually got two rejection regions. And we need to find out what those critical values are. Now we've got z sub c over here, and over here will be the negative of that. So all you need to do is find this one and just put a negative number on that one. So your rejection region will be z sub t greater than z critical, or, because you can reject it two different ways, or your test statistic shows up over here and it's less than the negative z critical value. And remember, once more, to get the critical value, you're going to use inverse normal. But remember, the alpha is 0.05 and it's a two-tailed test. So 0.05 has to be split between this area and this area. So we're going to use alpha over 2 for this. In other words, we're going to use inverse normal, and half of alpha is 0.025. We'll work with z's, so it's 0, 1, and you'll find your critical value. And our critical values will be 1.96 on the right and negative 1.96 on the left. If our z-test statistic shows in here, we reject the null. Or if it shows in here, we're going to reject the null. It's the value that shows up here, or here, or here. If it's in the rejection regions, we'll reject the null hypothesis. So to reiterate, calculate the standardized test statistic now. I like to call it this. If it's in the rejection region, reject the null. If it's not in the rejection, fail to reject the null. That's pretty simple, right? And there are three pictures again. Remember, these z sub zeros are what I call zc because these are critical values of z. And we're going to compare our test statistic against those. This is our test statistic here, 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 and here for the various tests. So, stepwise, check to see whether you know the population standard deviation. Is the sample random? And also important is, are we told that it's normally distributed, or do we know that have we decided on a sample size greater than 30? Once we've got that, decide what the claim is. Write it mathematically and its complement. Identify which one's the null. That's the one that has equals in it. The alternative is the other one. State those, and don't forget to label which one is the claim. Excuse me a sec. Specify the level of significance. Remember, this must be done before we actually collect our data. Find out what the critical values are. And those critical values depend on what alpha you chose. You'll use inverse normal to get those z sub c value or values. This will be the test statistic you'll use to see whether this falls in the rejection region or not. So you write down what the rejection regions are. Better yet, have a picture too. Sketch it. Find out where this standardized test statistic lies. Does this lie within a rejection region or not? Then you make a decision. Do you reject or you fail to reject the null hypothesis? If it's in the rejection region, reject. If it's not, fail to reject the null hypothesis. And last of all, but most important, interpret that decision. And that's in terms of the original claim. Time to do some examples. Now we've got a claim here. We see that right off the bat. The claim is that the mean is less than one of its competitors. So claim mean is less than the competitors. And that would be 95,600. So we've got our null and alternate hypothesis. This is what our claim is. So we're going to use this after we find out whether we reject the null hypothesis. Next, it's a left-tailed test because we're thinking the salary is less than, and the level of significance 0.05. So we use inverse normal to get the critical value, which I call z, where's my cursor? Oh, z sub c. So we're going to be comparing it with negative 1.645. In other words, we're going to check and see whether the standardized test statistic is less than negative 1.645. Then it's time to calculate the test statistic. This is the value that we got from the competitors. We're going to subtract it. We're comparing it with 95,600. Here we've got our standard deviation, our sample size of 20, and here's our test statistic. Question is it less than negative 1.645? No. It's not in the rejection region, so we don't have any proof or evidence that it's different from the value that our employer says. Our employer says. And finally, good write-up. There's not enough evidence at the 5% level of significance, as opposed to the 1% or 10%, to support the employee's claim. So the employees are either going to have to get more information, or they're just going to have to forget about it. So the mean salary we can still assume is about 95,600. And you can pause and read that through. If it is different, it's probably due to a sampling error, which can happen. Our samples can't be perfect. Here's another one to try. Last example, I think. We've got the mean cost of raising a child between the ages of 1 and 3. And we're saying that the cost is $13,350. So the claim is it's $13,350. What's the opposite of that? And it's not. Which means it's going to be a two-tailed test. And the claim is that, let's see, let's double check here. Yeah, the claim is that is this. So we'll label this so we can write our conclusion in terms of the $13,350. We know the standard deviation, so we can use a z-test. It's knowing the population standard deviation that allows us to do this z-test. A quick tip for you, when we get to the next section in 7.3, that's where we don't know the population standard deviation. We can't do a z-test. And just to let you know, don't tell anyone, but we'll have to do a t-test in that case. But back to our problem. Our n, we've got a nice big sample. So even though it doesn't say it's normally distributed, the sample size being this says we can assume we can use the z-test. The claim is the mean cost is $13,350. So here's the claim as the null hypothesis and the alternate hypothesis. Two-tailed test because not equals. So before we can decide whether to reject the null hypothesis or not, we have to find out what the critical value of z is. Well, that means we're going to have to use inverse normal. Where am I? There we go. Inverse normal. Now, remember, the area goes here. Since our alpha was 0.10 and it's a two-tailed test, this needs to be alpha over 2. That's where we get the 0.05. And since we're using z's, 0 and 1 is important. So our critical value will be a negative 1.645. And the positive one will be 1.645. So the rejection regions are, is the z-test greater than 1.645, or is the z statistic less than negative 1.645. Those are our rejection regions. Then we pick up the standardized test statistic. I call them z sub t. Here's your sample mean. Here's what you're comparing it against. There's our standard deviation and the square root of the sample size. And there's our z test statistic. And we'll take this and see whether it's in either of those two rejection regions. Well, guess what? Right here, let's see, where's my cursor again? Okay, right here is the test statistic on the left. So this is the rejection region in here, and this is the z critical value over here on the right. This is the rejection region, and they're on the right. And the only question left is, where is the test statistic? Well, it turns out the test statistic is negative 1.89, which means it's in here. It is in the rejection region. So you reject it, and I would suggest, remember I showed you an alternate way of doing a z-test? Go to Stat, Tests, z-test, and fill in the blanks. And there is enough evidence. We rejected the null, so at the 10% level of significance, we can reject the claim. Because remember, the claim was equality. And folks, that's it. If it was confusing enough, go back and look at the definitions of hypothesis testing, and come back here and try it again, and then with the exercises. Have trouble? Two things. Come to my office and ask questions, or better yet, bring your questions to class, because someone else might have the exact same question. Well, that's it, folks. We've finished this section, except for the hard work. And I'll see you next when we won't know the population standard deviation. Oh no. But remember, I gave you a hint. In that case, we'll use t-tests. Until then, keep smiling.